The purpose of this lesson is to talk about query languages for databases. So as a first step, it's probably worthwhile to talk about databases, what a database is and how it works and what it does. Now, really what a database management system is a piece of software. And the purpose of that piece of software is to manage data for two kinds of customers. One kind of customers are applications, things like Amazon.com or a human resource system or a student registration system at the university. What this does is it allows the people who write the application to sort of forget about the data. They can say create new students and register students in courses and then print out student transcripts, all without having to worry about how the bits and bytes are stored on the disk. All the data is run by the so-called database management system. There's another class of clients, and these are users. And the vast majority of users never see a database. They, of course, go through the application, the human resource system or Amazon.com or whatever. But there are certain users, especially those whose job it is to access data and to create reports and to understand things. They can go right to the database management system and write their own queries. And that's really what we're going to be talking about in this lesson, is writing queries. Now the nice thing is that there's many different types of database management systems and many different vendors, such as the big ones, Oracle, IBM, Microsoft SQL Server. And there's also some really interesting emerging open source databases that provide very similar functionality. Now, the nice thing about all these databases is they do two things in common. First, when they're presenting data, they use the abstraction of a table. That is, when we're thinking about data, we don't have to worry about the bits and bytes. The database management system gives us our data as tables consisting of columns, things we want to know about like last name, first name, address, and then rows, which in this case would be, say, the individual customers about which we want to store data. So the first thing we have to do when we use a database is always be thinking in terms of tables or sets of data. The other nice thing about relational database management systems is that they all use basically the same language, some kind of query language. And we'll take a look at that in the rest of this lesson. Before we talk about query languages, it's worthwhile to consider the context of this lesson. So we're going to illustrate query languages with an order entry system. And all order entry systems are pretty much the same. In fact, orders haven't changed much in 100 years. So here's an example of a very old order. Now, at the top of the order, we have what we might call the order header. These are attributes of the order, such as the order number, the order date, the customer, and so on. And in fact, you may also consider the total order amount as an attribute of the order as a whole. Then we also have this middle section, which are transactions within the order. That is the order details or the line items. So in this case, multiple things were ordered as part of this order, multiple products, and each has a certain order quantity and a certain price. So from a database point of view, it's absolutely critical that you identify or recognize the one-to-many relationship implied by an order. That is, one order consists of multiple order details. And this will be the context of this lesson. To put all this together, let's consider a very simple application that ships with Microsoft Access. Now, Microsoft Access is a relational database, but it's not fully client server, so it's a bit of a toy. But at the same time, it's a very good teaching tool, and we'll see why. So say I go to this order entry application and I select orders. What the order screen allows me to do is enter a new order with a minimum number of keystrokes and a minimum amount of effort. So for example, if I create a new order, I don't have to remember my customer numbers. I can just pull down a customer from a list. And the database goes off and gets the name of the customer and the customer's address and so on and so forth. Now, when I add new items to the product, same kind of idea. I can pick an item, I can specify the quantity to order, I may want to give a little discount, uh, but the application does all the slug work of calculating the extended price, calculating the total price, um, and then of course printing the invoice and communicating with the customer. So really the point of the application is to process sales transactions. But at the same time, because it's a database application, all this data, all these orders are being written to tables in the underlying database. So for example, I have an orders table and I of course have a customers table. All this information is in the database and is available for some analysis. The first thing to know about the relational database model is that tables are designed in a certain way for a reason. To illustrate that, let's consider a very naive, a very poor table design. For example, here we have one column where we record the name of the company, that is the customer, and then we have the order date, and then we have the name of the product. Obviously, this is going to be very inefficient. For all the products ordered in that order, we'd have to type the customer multiple times. This is both a waste of disk space and a waste of time for whoever's doing the order entry. It also can create problems if there's mistakes. In the future, there's no way to match all the orders placed by Rattlesnake Canyon Grocery. A slightly more subtle problem is that we're storing unit price for every product. But if we store data this way in a big spreadsheet, where do we store the prices of products that are not in the order? This can be a really big problem. So for various reasons, we tend not to store data in this way. Consider an alternative table design. Here we have an orders table. It stores information about orders. But rather than store the customer or the name of the customer, we simply store the customer's ID, a short little number, an integer. Then, elsewhere in the database, we have a table of customers, and each customer is uniquely identified by a customer ID. So in principle, it should be possible for every order to find the customer ID and then go to the customers table and find the corresponding customer and all the information about the customer, like the customer name, shipping address, and so on. So for the orders table, we say that its primary key, that is the field that uniquely identifies the order, is order ID. And for the customers table, we say that the primary key is the customer ID. But to make this relationship between orders and customers, we take the primary key from the customers table and put it into the orders table. We call this a foreign key. This foreign key allows us to implement the one-to-many relationship between orders and customers. Good table design has a consequence for relational databases. What we tend to end up with is a lot of tables, hundreds, thousands, tens of thousands of tables, each storing information about one thing, about customers, or about orders, or about those order details. Now this isn't a very efficient way to store data, and it's optimized for transaction processing. That is, adding new transactions, adding new data. Where it becomes difficult is for someone who wants to extract data to answer a question. Then you have to navigate this web of many tables and relationships. Let's step through how a query language allows you to navigate a relational database system and get what you want. So you start with normalized tables, that is, these single item tables like customer and order. Then you have a query language processor. Typically, the most common of these is what's called structured query language, or SQL, or SQL, doesn't really matter. Although increasingly, a lot of tools have graphical query languages. These vary by software product like Tableau or Microsoft Access or even SAS, but they're all very similar. Structured query language, on the other hand, has the virtue of being highly standardized. Once our query is run or executed by the query language processor, we end up with a result set or view. This is like a virtual table. It's created dynamically by the query processor, and although it looks like a table, it's not stored anywhere in the database. It's built from the data taken from multiple tables and multiple locations. To demonstrate the use of a query language, I'm going to use the data from the Northwind Traders sample application, and I'm first going to look at it using the query by example interface in Microsoft Access. Now, the nice thing about query by example is that it's visual, and as I said, it's similar to almost all visual query editors. Then I'm going to do the same tasks using good old-fashioned plain SQL on a MySQL database.